So today let's try to fix this function generator I came across recently. It's partially working, it sort of is usable, but it has some problem that definitely would be better fixed. And this function generator or signal generator can generate a square wave, a triangle wave, or a sine wave, but also this sawtooth with a faster rising or faster falling edge, and non-symmetrical square waves with longer off time and longer on time. And the frequencies can go from surprisingly low, 0.0001 Hz, all the way to 1 MHz. This switch sets the frequency in steps, and then this is a continuous adjustment from times 1 to times 10 this. Here's the power indicator LED. You can set a DC offset on top of the signal, and here is the output, and here is a fine continuous and stepped selector of the amplitude. Here is the back of it with the mains in, the power switch, the fuse, the voltage selector, some trigger output and whatever that is, voltage control the frequency or something. And it's made in Hungary, I guess in the 80s. And this thing is easy to open, it has just 2 screws holding the top, and then the top cover just slides out. And the voltage selector can select 110, 220 or 127 volt mains voltages, but the previous owner seems to have modified it for 237 volts. Because nowadays the European voltage is 230 volts nominal, and the actual mains voltage is often close to 240 volts. And of course here you can see the internals of the power supply, and here is the power transformer with the primaries and secondaries. And the primaries of the transformer are 110 volts, another 110 volt section and a 17 volt section. And there is a voltage selector which can choose different combinations. The 110 volt windings in parallel for 110 volts, or this parallel combination with added 17 volt winding for 127 volt mains, or the 110 volt sections in series for 220 volt mains. But the selector can't select 237 volts. So the previous owner seems to have rewired the windings like this for 237 volts to prevent overvoltage on the secondary winding and the transformer core from getting too hot. Because typically 5% extra primary voltage causes about 25% extra heating in the core of the transformer. I think this modification is a good idea. It definitely didn't cause the problem in it. And the power supply has 2 main smoothing electrolytic capacitors here. One of them seems to be replaced, it's a modern capacitor, and the other one is original old capacitor. And this was also done by the previous owner. I don't really see any other obvious modifications in it, it seems mostly original. Other than these 3 OpAmps in these sockets, 8-pin chips basically in 14-pin sockets. Not sure what this is meant to be. They seem laser printed, they seem modern to me, not original. All 3 are 741, very common OpAmps. I guess the OpAmps are replaced, but the sockets seem original. They look very old school, not like modern ones. But now let's actually demonstrate the problem of it. Here it's making a nice sine wave. Now it's set to 1 MHz, and it actually is about 1 MHz, 100 kHz, 10 kHz, 1 kHz, 100 Hz, 10 Hz. 1 Hz is already slow rolling. The triangle wave, square wave, non-symmetrical one, and the other one. Sawtooth. This looks nice. You can set the amplitude, of course, and the fine setting. Here's the DC offset. This also works. Everything seems to work as long as I keep this knob in its upper setting. When I reduce the frequency, it's reducing nicely all the way to 5, and then something strange happens. It's increasing only the off time, not the on time. You can see here it's changing both times equally, it's 50% duty cycle, but from some point on it suddenly increases just the off time, not the on time, which is weird. And for the sawtooth, it works in the upper range as well, and When I go down, it suddenly increases the length of just the rising part, not the falling part. And it's probably because all the waveforms are generated from the same thing initially. When I go to a sine wave, you can see it's a nice sine wave with the knob in the upper part of the range. And when I go down, it starts distorting, and now it's quite a distorted sine wave. Also some other waveforms. And this one is meant to be faster rise, and it suddenly flips into a faster fall here. And the problem always shows up in the lower half of this knob range. And this problem also seems to be completely frequency independent. This is happening the same in all positions of this switch. Again, in the lower part the sine wave distorted, in the upper part not distorted. Another range, upper part not distorted, lower part distorted. It's not affected by this switch or anything else. It's completely frequency independent and waveform independent. And the offset or amplitude also doesn't change anything about it. It has to do something with this control. The upper part nice sine wave, the lower part distorted. And of course in an old device you'd suspect first some capacitors, but this problem is completely frequency independent. It basically happens in the lower range of the knob, no matter if it's like 1 Hz or 100 kHz, so it can't be a capacitor. Of course this decade selector has several capacitors connected to it, but each of them is just for one position. If it was a bad capacitor here, it would only affect one position of this decade selector. Of course the non-symmetrical waveform in one half of the range of this potentiometer made me think there is some problem in the potentiometer, but I was thinking it's a double potentiometer with one section not making contact in the lower half or something, but this is just a single potentiometer, not a double one, not two potentiometers on one shaft. So I don't really see this potentiometer causing the problem. Another very common problem, especially in older devices, is poor contacts in these switches, but again the problem is happening in all positions of them. Theoretically it could be one story of these multi-story switches not making contact in any position, but this makes contact in all 4 stories of it. And this 5-story rotary switch also seems to work everywhere. I measured it. Of course now it's off. And using my old multimeter, let's check the voltages in this thing. It has a symmetrical power supply, and the positive rail before the regulation is about 24 point something volts. And the negative rail before the regulation, again 24 point something minus. And of course typically OpAmps are using a symmetrical voltage plus and minus 15 volts. Let's check it on these 741 OpAmps. The pin 7 is the positive, I guess. 15.09, nice. And the 4th pin is the negative, I guess. 15 point something again. This seems right. If the supply voltage was wrong or non-symmetrical, if one of the rails was off, it could cause this problem, but it doesn't seem to be the case. And this potentiometer seems to be right. The slider is making contact in all positions, it seems. This seems good. Because the problem is frequency independent, it doesn't depend on the position of this decadic switch. It can't be any capacitor or inductor. It has to be something like a resistor or some semiconductor like a transistor, chip or diode. Of course resistors are the least common thing to fail, especially the low power ones. It could be a poor contact in some of these adjustment potentiometers on the board or trim pots. There is a lot of them. There are some smaller ones also. But it could also be somebody just randomly turning the potentiometers in it. And this is like the worst you can do, just randomly turn everything without knowing what it does. And of course this thing is bloody complex. I counted about 58 transistors in it, plus 4 OpAmps, 3 plastic ones here, plus this package. This metal can with more pins than a transistor. It's not easy to wrap your brain around what you can use almost 60 transistors for just to generate a waveform. The complexity of this device is just unbelievable. Now let's try some dumb techniques, like tapping these trim pots and watching the distorted waveform, if it maybe changes or improves, or maybe the OpAmps have a poor contact in the sockets. There could of course be some mechanical problems, some poor contacts, bad solder joints, trying to flex the board a little bit. if it has any effect, or basically tapping the thing. And there are 3 identical op-amps, who if I try to rotate them, this one goes here, this one here, and this one here. If some of them is bad, moving them around will change it somehow. If it doesn't work, I will return them into the original positions because they might have offset null potentiometers for them. And then each of the potentiometers would be specifically set according to the offset of the particular op-amp. I rotated them and no change in the waveform. Let's poke it with a paint brush. Maybe this could reveal some poor solder joint of some of the components. And there are 4 power transistors on a heatsink. And this is the power supply and 2 small transistors with small heat sinks. This is the pair of output transistors, I guess. And the bottom cover also is on 2 screws and the slide is out. And here's the circuit board. Mostly just tracks. Few resistors bodged here. I visually don't see any bad solder joint. And I forgot to show this resistive network on the attenuator from 0 to minus 60 decibels. Here is the replaced capacitor bodged in. Again poking it with a paint brush. Maybe it will affect some bad solder joint and show up. No change in the waveform. It seems I ran out of completely brainless diagnostic techniques. Now it's probably time to start thinking about it. Of course I could completely randomly measure all the transistors and resistors in it, without knowing what they do. I already measured the diodes in it and they seem fine. But instead of trying to measure all components in it, let's try to look at the schematic and understand it a bit. And I have to warn you, this is going to get complex, so have a fire extinguisher ready if your brain catches fire. And the schematic of it is on 3 papers. And the first one is the power supply, and just the power supply contains 14 transistors in it. And it also has plus 6 and minus 6 volt rails, which I didn't even know about. And it has 5 fuses in it, and by the way, 3 out of 5 were wrong values. It's always fun to see what desperate people do when changing fuses. And here is the first part of the main schematic, and I found it on some German website. Somebody was drawing into it. Here is the fine frequency potentiometer, the 3 op-amps, then some integrator producing a triangle wave, and this circuitry turns it into a square wave. And the square wave also goes to the trigger output. And the triangle wave goes to point A and the square wave to point B, which continue to the second part of the main schematic. And in this one, these 12 transistors are just to produce the sine wave. This is a crazy contraption. Basically the triangle waveform goes in, then a miracle happens, and then a sine wave comes out. This is only used for the sine wave and for nothing else. Otherwise this waveform switch gets directly the square wave or triangle wave and sends it into this fine amplitude potentiometer and this amplifier. These are the transistors with small heat sinks and then this attenuator resistor network. The amplitude switch can choose this straight connection or 6 different resistive dividers. But based on the behavior, we can rule out the amplifier and this attenuator. This is working well. If there was a problem, it would be distorting the waveform, not just in some positions of the fine frequency potentiometer. And we can also rule out the problem is in this sine wave shaper, because the problem appears in other waveforms too. And of course it looks crazy to use 12 transistors to make a sine wave, but a simple circuit could produce just a narrow range of sine wave frequencies. And of course you can also turn anything into a sine wave using several succeeding low-pass filters, but this would also be quite frequency dependent. And this triangle wave to sine wave converter has to be frequency independent. But anyway, the problem is not on this page. Let's go back to the other one. And there is this weird voltage-controlled frequency thing with the op-amps and 2 transistors and a lot of diodes. And the frequency can be controlled using the potentiometer or the voltage-controlled frequency input. I will go back to this insanity later. And from this insanity it goes into this integrator, which is using the metal can op-amp. And basically the signal goes via resistors into the inverting input of it, and there is a negative feedback from its output through a capacitor into its inverting input. Of course the frequency decay switches different capacitors and different resistors here. For the slowest it's using 2 15 mega ohm resistors in series. But this op-amp is used in the integrator just for 1 kHz or lower ranges, but for the highest frequency ranges above 1 kHz, which is basically the top two ones, 10 and 100 kHz, it's doing the integration not in this op-amp but in this transistor contraption, probably because the op-amp is too slow for it, and because it's using two different integrator circuits for different ranges, and the distortion happens in all ranges, we can simply rule out the entire integrator circuitry, both of them, both this discrete integrator and this op-amp based one. And the integrator basically produces a triangle wave, and I guess when the triangle wave hits the peak, it flips this discrete comparator, which is then reset using this resetting circuit, and then there is some bistable multivibrator, and the square wave comes out of this to the trigger output and also to the point B. And I was initially thinking this thing with the op-amps is an oscillator, but it's not, because from the point B there seems to be a feedback going back into this, and this is what makes it oscillate. The feedback from this square wave from the point B goes via a 510 ohm resistor back into the input of this integrator, or this one. The output of the integrator is basically either rising or falling, and when it hits the target value, this thing flips and also flips the input voltage. So the op-amps are not an oscillator, they are part of some voltage-controlled frequency contraption, and they basically reduce the voltage coming through the feedback. They pull the voltage down after this 510 ohm resistor precisely to some specified level. Of course, the lower the feedback voltage is pulled, the lower the frequency. And it has to pull the voltage down after this resistor in both polarities, in both half cycles, and the negative half cycle is pulled up to a lower negative level using this NPN transistor, and the positive half cycle is pulled down to a lower level using this PNP transistor. And these transistors are controlled using these OpAmps, and they are somehow connected to this frequency control potentiometer, which basically just controls a voltage. There is no AC on this potentiometer. It produces a negative voltage, and a positive voltage of the same magnitude is produced using the third OpAmp. So this is just the polarity inverter for the control voltage, and these two control the transistors, and this basically reduces the voltage coming from the feedback to a specified level. And of course, the lower the voltage, the slower the capacitor in the integrator charges, and so the lower the frequency. At least I think it works this way because it's bloody complex. This is something you have to keep staring at for a long time to get it. I don't think the problem is anywhere here, because the square wave coming out of it is symmetrical. I mean voltage symmetrical, not time symmetrical. The voltages in the positive and in the negative half cycle are the same magnitude. If they were not, this would influence the duty cycle here, but given the positive and negative half cycle is at the same amplitude, this has to be working right, and I guess the problem has to be somewhere here. And another reason for this is that it only happens in some positions of this potentiometer. But because rotating these op-amps had no effect, it could be some of the diodes or transistors, but I already measured the diodes here, so this is almost shrinking down to just these transistors or maybe some resistor, but low power resistors don't fail often. These two transistors, TR-15 and TR-16, are the most suspicious now. And by the way, these sections of the waveform selector can select the non-50% square wave or the sawtooth with the faster rise or faster fall. After looking at the schematic and thinking about what could cause this specific problem, the most suspicious are these two transistors next to the op-amps. And the third one is the voltage inverter. A closer look, here is the transistor TR-15 and the transistor TR-16. Let's measure them on the other side of the board. This one is NPN, base to collector, 0.6 something volt voltage drop, nice. And the other junction base to emitter, again almost 0.7 volts, seems right. And the other one is PNP, collector to base, 0.6 something volts, seems right. And emitter to base, 0.86 volts. This is a little bit too high, this is sort of suspicious. 0.7 something would be still sort of okay, but over 0.8 is strange. I think I'm going to desolder it. And by the way, it seems that very old 741 op-amps actually were 14 pins and a lot of pins unused. That's the reason for the 14 pin sockets. Here's the transistor desoldered, and measuring it using the multimeter outside of the board shows exactly the same thing. And using my primitive transistor tester, it actually seems to work normally, like a PNP transistor. And putting it in this transistor tester, it identifies as a good PNP transistor gain 118, but the voltage drop base to emitter is 1.4 bloody volts. More than double of what I would expect. There is just something sinister about this transistor, and the marking of it looks completely different than the other transistors. All the other transistors seem to have paint marking, which is vertically on them, and this suspicious transistor seems to have a laser marking which is horizontally on it. Was this transistor already changed? A lot of the transistors in the board are the same type, but they look like a different maker and a different year. And for comparison, a very common BC327 PNP transistor, and it shows just 0.6 volts voltage drop base to emitter. I'm going to put this transistor into it just to see what happens. It shouldn't be that critical, it's just a tiny PNP transistor, and it's silicon, not germanium, so it should be easy to replace using modern transistors. I just horribly botched it on the other side to see what happens. And testing time. And it seems to be a nice sine wave everywhere. No distortion. In the lower half of this fine frequency potentiometer where it was previously distorted, now it's not. It makes nice waveforms. The square wave duty cycle should be 50% and it's 52.3. And this is probably because the new PNP transistor is not matched with the NPN transistor in it. And they probably have a slightly different base to emitter voltage drop, and that's why it's slightly off. And it shows up the most in the lowest positions of the frequency control because the voltage going into the integrator is the lowest end, so a tiny difference in the voltage drops will skew it a lot. On the other hand, at higher positions of the potentiometer, it's less off, because the voltage is higher going into the integrator, and now it's just 50.3%, way less off from 50%. When the voltage going into the integrator is higher, it's not skewed as much by the imbalance in the voltage drops of the transistors. Of course, I can adjust the duty cycle by turning the offset null potentiometers of the OpAmps, but this is not the right way of fixing it. And these two transistors are meant to be a PNP and NPN complementary pair, with very similar base to emitter voltage drops and a similar gain. Now it's almost right, and when I put a better suitable transistor into it, it will be even better, so let's call it fixed. And the original transistor looks somehow cracked. This is weird because when a transistor is cracked, typically means that the internals are completely blown apart in it. But how this one is still working partially. This is definitely a very weird transistor failure. And I did some frequency and duty cycle alignment. And the dial of the fine frequency potentiometer is adjusted using these trim pots. This one for the highest, this one for the lowest, but they affect a little bit the opposite, so you have to iterate several times. I also adjusted the offset null potentiometers of the 3 OpAmps for 0 offset. And then I adjusted this offset null potentiometer of this metal OpAmp in the integrator, and this offset null potentiometer of the discrete OpAmp for 50% duty cycles. And of course for this one it's done in some range other than the highest two, and for this one in the highest two ranges of the decade switch. And in both cases with this potentiometer at minimum, where the offset affects the duty cycle the most, of course. And I decided not to touch the other potentiometers in it. Of course, the final amplifier could be somehow aligned for minimum distortion, and the potentiometers could be aligned in this sine wave contraption, looking at a Fourier transformation and minimizing the harmonics, but I think this is already over the top. I managed to adjust it right with the wrong transistor in it, so it's not extremely critical, it seems. And now it's working basically as good as I can imagine this 40 years old thing working. And of course this video got bloody long and bloody complex. But if you survived all the way to here, please consider supporting this channel on Patreon, using the thanks button or subscribing, because you're apparently one of the most intelligent viewers. Most of them probably died somewhere mid this video, of course. And big thanks to all of you who already support me. And here testing it together with the trigger output.